Welcome to my channel. So we are asked to solve this problem, which is a simple problem, but it has a very interesting solution. We have a particle of mass m, which experiences a constant conservative force field directed parallel to one of the two axes. So here, let's illustrate the problem. We have, let's label x and y. So the force is parallel to one of the two axes. So let's just say that the force field is parallel to the y-axis and it's either going up or it's either, or going down. So and this is a constant magnitude everywhere, anywhere. It doesn't depend on y if it is parallel to y-axis. So find the equation, both algebraic and parameterized forms. So I will explain later what are these algebraic and parameterized form of equations of the trajectory of the particle, assuming that r0, this is the vector, meaning it starts at the origin, and the initial velocity is u naught. This is a constant vector. Okay, so here u naught is means that it's a constant vector by using the principle of least action, meaning that we have to solve it from the action itself. Okay, so to start with the action, we have to form the Lagrangian, which is equal to T minus V. Here, our kinetic energy is equal to 1 half times m, 1 half m times x dot squared plus y dot squared. That would be m. And okay, how do we determine our potential? So theoretically, our potential is actually defined to be the negative integral of f times, in this case, our f is a function of y alone, dy. Now, what is the limit? It's actually starts from a reference point. Let's call this y ref, or um, how do you write this one? Just capital Y. Y ref to some point y. So, what is y ref? This is our point, our zero potential reference. It can be anywhere. We can set the zero potential here or here at different y. So this is why, okay, again, I'd like to emphasize y rep is the reference point, meaning that at this level, our potential energy is zero. So this is now our v of y. So in this case, this is equal to the minus the integral of y ref from y of alpha dy. So this makes our potential v of y as equal to negative of alpha y minus y ref. So we now have that. We can now form our action as to be the integral of 1 half m x dot squared plus y dot squared minus v, so plus alpha y minus y ref d dt. Okay, from point 1 to point 2. Now y ref here is a constant. Okay, it's not a function of y. Okay, so the principle of least action means that we take now the variation of this and set this equal to 0. Taking the variation of this action, this would now have m x dot delta x dot plus m y dot delta y dot. We just apply the variation in its term. And here, that would be alpha delta y, the integral of that, dt equals 0. Okay, so let's find this one. What is x dot delta x d over dt? This is just equal to first the second, so x dot delta x dot plus x double dot delta x, and similarly we have d over dt of y dot delta y, that would be y dot delta uh, y dot plus y double dot delta y. So we can now replace this one here by this minus that, and that one by this minus this, and I'll separate the integral. Okay, so I would now, my integral now becomes, okay, the integral of d over dt x dot delta x dt, I separated this already, plus, because we have this minus that. Okay, I'll write this one first. The integral of d over dt of y dot delta y plus the remaining terms here, in which we have the integral. Okay, this is evaluated on point 1 to point 2, and since these two are negative now, so we will I'll write this one first. We have alpha delta y minus, it becomes x double dot delta x minus y double dot delta y dt equals 0. Now, the integral of this is just equal to, that integral there is just x dot delta x evaluated from point 1 to point 2, plus the integral of that is just y dot delta y evaluated again from point 1 to point 2. Now, plus this is alpha, alpha minus, okay, there should be m here. We should be putting m. There's m there. Alpha minus my delta y minus mx dot delta x dt equals 0. Now, this is 0 because delta x is 0 at uh, at um, at the boundary, no, at p1 and p2, and as well as delta y is 0 at p1 and p2. So this is 0. So what is left is this term here, and meaning that this must be 0 inside. And since each of these are independent, x and delta y are independent, now we can set each of the coefficients, okay, because this will form now a linearly independent set of uh, the vectors. So meaning that this one whole thing is 0 and that whole thing is 0. So I would have now two differential equations. First equation is, sorry, this is m. Okay, the first equation is alpha minus m y double dot equals 0, and the second one is you have mx double dot equals 0. So here we now arrive at our differential equation, and once we solve this, we now have the solution to our problem. Okay, so let's start solving that. Mx double dot equals 0. From here, clearly, we can see immediately, integrate, this is actually x dot dx dot, because x double dot is dx dot over dt equals 0, implies that x dot now is equal to some constant. Let's call this constant c1. Okay, now notice that this is x of t. Okay, this is x dot of t. So we have to apply the boundary conditions to solve for the constant. What's the boundary condition? R dot not R dot z R dot of 0 is equal to u naught initially. Okay, now let's analyze this u naught. Okay, we are here at r at t equals 0. We are here, and u naught is this vector here. This will be our initial velocity. Now, meaning that here this is u naught x, and that would be u naught y. It will now be practical to express to find u naught y and u naught x in terms of u naught through this angle here. Okay, theta. Let's define this angle theta, and we can just call it the initial angle, so that u naught x is just u naught cosine of theta. Okay, so the x dot at 0 is equal to u naught cosine of theta. So, and this is equal to C1. Okay, meaning here that C1 is u naught equal to theta. So here, our x dot of t would give us u naught cosine of theta, meaning that it is constant all throughout. It doesn't change. Okay, the velocity is constant. Velocity in x is constant. It's not even a function of time. Okay, so again, since this is equal to dx over dt, we can directly integrate our x to find our x of t. This will now be equal to u naught cosine of theta times t plus c2. How do we determine c2? Again, let's apply the boundary condition, the initial condition. Okay, it is at 0, 0. Okay, this is the 0 vector. So at t equals 0. From here, setting this equal to 0 and this is equal to 0, we can see that C2 is just 0. So our x of t is just this. Okay, now let's solve our y of t. Okay, we have this alpha minus md squared. Okay, sorry. I'll just dy squared dt squared equals 0. Or this is actually equivalent to alpha minus m dy dot over dt equals 0. Integrating this, okay, what do we get? Uh, we have equals alpha. Okay, now when we integrate this one, we see now that our y dot of t is equal to this a dt alpha over m dt. So that will become alpha over m t plus, okay, we have c2. I'll use c3. Okay, and apply again the initial velocity. Notice that y dot of 0 is equal to this one, u naught y, which is u naught sine of theta. So we can think this is u naught sine of theta. Um, and if you substitute it here, you will see that C3 is just equal to, this will be equal to C3. So our y dot of t would be equal to alpha over m t plus u naught sine of theta. This is a constant here. And again, this will be our dy over dt. We can now solve for our y of t. So y of t, integrate this, we will have alpha over 2m t squared plus u naught sine of theta times t plus c4. Okay? And again, apply the boundary condition. The boundary condition states that at y of 0 is 0. So this would make C4 equals 0. From here, applying the boundary condition y of 0 equals 0 implies that C4 equals 0. So we now have our y of t. Y of t equals alpha over 2m t squared plus u naught sine of theta t. Okay, Now, how do we write? This is actually the parameterized form of our trajectory. In physics, once you solve the differential equation, you get the solution will be a parameterized equation. If you get solve the second order differential equation with respect to time. Okay. Now, to find the parameterized, the algebraic form of the parameterized equation, all we have to do is actually from here, from there, we know that t is equal to x over u naught cosine of theta. So, and then substitute x here. So, this is now our y of x. It's no longer y of t. So, this would be alpha over 2m times x over, that would be x squared over u naught squared cosine squared theta plus u naught sine theta over u naught cosine theta. That is cancel ang u naught will cancel. Sine over this tangent. This is tangent theta. This is x tangent theta. So our equation now, y of x, our algebraic form would be equal to alpha over 2m u naught squared cosine squared theta x squared plus tangent theta x. Notice that it is a parabolic path. Okay, we would expect a parabolic path, and depending on the direction of alpha, okay, let's investigate this. What if alpha is negative? If if okay, if alpha is positive first, if alpha is positive, this will be positive, meaning that it's opening. And where does the vertex of this lie? We can calculate actually the vertex, find b. The vertex is just vx, the vertex, the x component of the vertex, that would just be equal to minus b over 2a. So that would be minus tangent theta over 2a. Well, it is somewhere, okay. Anyway, it's quite messy to solve that. Okay, you can solve that on your own. You solve the vertex v. I no longer have space here. So if alpha is greater than 0, then it will be opening up. Okay, so if alpha is greater than 0, maybe the parabola is going that way, this way, because since at 0 it's actually going upward, so the parabola is around here. The vertex is on the left. Okay, how about when alpha is less than 0? If alpha is less than 0, it's negative, then uh, that would mean that the only way to construct a parabolic path here is this will be the parabola. And it will look now familiar to you what this one is. Okay? Again, if alpha is positive, this will be our parabola. This is the only way that we can have a parabola here because initially it's going up, meaning that the vertex is somewhere in the on the left. Okay? Now, if alpha is negative, okay, since we are actually going up here, so meaning that since the parabola must be opening down, so the vertex is yet to be reached. Okay, since the parabola is opening down, if alpha is negative here, alpha is negative, then this whole thing will be negative here, so that the vertex must lie somewhere on the first quadrant. Okay, here, if alpha is positive, then the vertex must lie somewhere in the third quadrant. Okay, now this will now look familiar to you, and in fact, indeed, it looks familiar because if I'll just set alpha equals minus mg, see what would happen to y of t. Y of t now becomes, this is now u naught sine theta t minus 1 half gt squared, the x component of the projectile motion. And what would happen, okay, what would happen to x of t? X of t now would be equal to still the same. It's not affected. Okay, u naught cosine theta t. This is the equation of motion of a projectile motion. Okay, projectile motion is a constant force field directed on the negative y. It's exactly like this, but the direction is always going down. That's why this is actually the I mean, where the projectile, the initial angle in the language of projectile motion, this is the initial angle theta, and it's going uh, uh, up, and then it will start to slow down and then eventually stop in terms of the velocity along y and just uh, follow the parabolic trajectory. Okay, this is the maximum height, in which the maximum height is actually the vertex of that parabola. Okay, if you have not subscribed yet, please subscribe. And if you think that I've committed some mistake here, some algebraic mistake or signed or whatever, sometimes I misspeak. I speak wrongly. I misspeak, and sometimes actually um, I commit some algebraic errors. So feel free to comment. I'm solving the problem on the spot. That's why there are times that I cannot check my answer. Okay, so feel free to comment your correction if there are any corrections. Thank you for watching, and please subscribe.